Hi everyone, this is Jude, and in this video I'm going to test all 8 operations in my ALU circuit for demo 9. First is subtraction. I'll leave the select input to at 0, which right here tells us 0 is responsible for the subtraction of a minus b, and I'm going to set a equal to 7, and binary is 0, 1, 1, 1, and b to 2. So it's going to be 7 minus 2. The output is 5, which is in binary 0, 1, 0, 1, which is correct. Now for mode 1, the mode 1, what it does is add a plus b. So if I switch this to mode 1, it's going to change our output to 9. It's going 7 plus 2, which is 9. Or we can do 7 plus 3, which is 10. In hexadecimal, it would be a. Now, for mode 2, it's going to be multiplying the least significant 4 bits. That's what it's going to be outputting, the least significant 4 bits of a multiplication. So let's set a equal to 3 and b equal to 2. And then let's switch the mode to the second one by clicking the select input. And as you can see, it says 6 right here, which is correct. The output is 3 times 2, which is 6. Now, if we were to do mode 3, which is multiplying the most significant 4 bits, we might need a bigger number than this, since the most significant 4 bits would only be for bigger numbers. So let's try setting a equal to 8 and setting b equal to like 4. So 8 times 4 is 32, is showing the 2 right here, which is the most significant bit. In binary, it's going to be 00100000. So that's what it shows. It's the 4 most significant bits. And that's what we got. So for selector number 4, it's going to be dividing. So let's divide 9, let's say 9 by 3. That gives us 3. 9 divided by 3 is 3, which is correct. Same thing here in binary, it's given us 3. And then for selector 5, it's going to negate a using 2's complement. So I'll set a equal to 6, and as you can see, it doesn't matter what value we have here in b, because this is only going to negate the a value. So basically, 1's complement would switch this to 1, 0, 0, 1, but since this is in 2's complement, we add a 1. So 1 plus 1 in binary is 1, 0. So this is correct. And for selector 6, mode 6, it's going to be doing the bitwise AND. Let's set a equal to 10, okay, and let's set b equal to 7. So the result is giving me 2. Now, you would think that this is going to multiply, but actually it's only going to give out the value where if both a and b are on. So as you can see right here, it's only on when at 2. This is 1, this is 1, but when it's at the first one, it's 0, 1, and the third one is 0, 1, and the fourth one is 1, 0. So it would only give you the output of whatever 2 bits are matching if they're both on. So let's turn this one on, it's going to give me 3. If I turn this one on, it's going to give me 7. If I turn that one on, it's going to give me 15, which is F uh, in hexadecimal. Now for mode 7, finally, it's going to be the equality comparator. So if a is equal to, let's say, 0, 1, 0, 1, and b is equal to 0, 1, 1, 0, the output should be 0. But if I set both a and b to 0, 1, 0, 1, it's going to output 1, which means they're equal. So yeah, this ALU handles 8 different operations um, using using select lines and multiplexers to switch between them. Over here is my ALU Mini. Uh, it's got everything built in: the adder, the subtractor, the multiplier, the division, the second negation, and the and the equality comparator. The mux just picks the one we need based on the mode. So that's why I'm using muxes here. Uh, I made it this way to keep the design clean. Instead of building 8 separate circuits, I can bind them all into one block. So it's easier to manage and expand. If I wanted to add more operations later, I can just hook up a new module and extend a mux. Um, that's the wrap up for the ALU demo. In the next video, I'll show how the full microprocessor works using the controlled logic. And thank you for watching.